Okay, hello everybody, and welcome to this presentation on environmental testing, which is brought to you by Consumer Electronics Test and Development magazine in association with our lab. My name is Paul Willis. I'm the associate editor at the magazine, and before I introduce our speaker today, João Pereira, I want to just tell you a little bit about the format of today's presentation. So first of all, João is going to speak for about 15 minutes, giving the presentation, and then he and I will have a conversation at the end of that, and again about 15 minutes. And then for the last 15 minutes, we're going to do a Q&A, which you are invited to contribute to. To contribute to that Q&A, you'll see that on the right-hand side of the screen, there is a section there where you can add questions. So as you're listening to João, or if you already have any questions, please just write them in there, and then we'll try and get to them at the end. There's also going to be an interactive poll. There's going to be 4 interactive polls that you're going to see that you can contribute to as well. And we'll close those polls at the end of the presentation, and then João and I will probably refer to them during our conversation. So without further ado, I'm going to introduce you to João. We're going to be talking today about environmental chambers and the vital role they play in testing consumer electronics. And leading this presentation, we're very lucky to have with us João Pereira, who is the commercial director at our lab, a global supplier of climatic chambers. So with that, I'll hand everything over to you, João.
Well, thank you very much for the introduction, Paul, for explaining the mechanics of the presentation today. I'm going to go into what I've prepared for this session, and I'll be happy to answer any questions that you may have in the end. So, the title of this today is Designing Reliable Consumer Electronics and how environmental testing can prevent field failures. So, a lot of what we do at our lab is simulate climatic conditions so that the users of our chambers may simulate as best as they can real-world scenarios and anticipate product failures before they happen in the hands of the customer, which is something that everybody wants to avoid, right? So before going into the testing and the detail of the presentation today, I just want to take a couple of minutes to present you at a lab. So we were based in Portugal. We were founded in 1985, so last year was our 40th anniversary. And from the beginning, we are experienced in creating simulation for temperature, humidity, light, airflow, and among other environmental conditions. We try to get the best possible equipment in the hands of our users so that they can in turn develop the best products that they can. So currently our global presence is 82 countries. So it's likely that most of our audience today also has a local Art Lab representative nearby. So if you want to reach out in the end of the presentation, feel free. We'll be happy to share the contacts of your local support structure. Okay. Also let you know that we do at Art Lab, we do a wide range of applications, which oddly enough, sometimes cross themselves. There's paths that cross several applications. So we do plant research and life sciences as a whole. So chambers to mimic the sun, the temperature, the light, CO2 concentrations, and so on, to get the most accurate growing conditions for the plants. Also pharmaceutical stability, so these have to do with determining the shelf life of the medicines that we use every day. And then lastly, environmental and temperature or climatic simulation as a whole for a very broad range of industries, one of which is electronics. But electronics also has touch points with many other industries: automotive, aeronautical, HVAC, vibration, and so on. Okay. So going into the detail of our presentation today, I think there's a big question, which is what happens to the products that we use every day when we test them under extreme conditions. And not only extreme conditions, but also what happens when we test them under real world conditions. So what is an acceptable damage level of damage? What is unacceptable? How do we determine both? Okay. And the short answer is the way we do this is we test them. Okay, so we have to evaluate resistance, durability, of course, and this is how we determine quality and we ensure compliance with standards. Okay, so everything that we use every day in our daily life, from the mechanical door lock in our door to the chair we're sitting on to the PC where we're watching, or cell phone where we're watching this conference, everything is tested all the time. Okay, so of course we simulate extreme environmental conditions, ensure product safety, durability, and performance. So we have to ensure that the products do what they say they do, and we have to make sure that they do that in a safe manner. Obviously, meet industry standards and regulatory. I've just mentioned pharmaceutical, for example, but I can mention aeronautical or automotive, where there's industry standards that we must adhere to. And then I would say the main objective is to prevent failures and reduce costs. So if you can think of automotive industry, the cost of recalling tens of thousands of cars, not only the direct cost, but also the brand impact that the recall like this may have. This is something that manufacturers avoid at all cost. And then finally, develop new applications. So support research and innovation. If you want to push the envelope with your products, you have to also push them uh, regarding the environment that they're going to operate in. Okay, so this is very, again, automotive industry, but also defense industry, for example, uh, electronics as a whole. I would say this is a very, very important and critical aspect. Okay. Now, when we go into the most common failure modes, and of course today, because of my let's say uh, professional career, we're going to focus on the ones that tend to be environmentally induced. It doesn't mean to say that there aren't other failure modes. Of course there are, but we're going to focus on the ones that are promoted by environmental conditions, which are the ones that we at Lab typically address. Okay, so the main one, or one of the most common ones, is corrosion. So accelerated degradation of a material, of course. Then there's electrochemical migration, moisture leakage, and condensation. So this is very typical when we have very fast temperature changes, and there is a sealed container, something that may uh, be detrimental to vapor exchange with the outside. So you may have condensations inside the product, which is something that typically users don't want to have. Okay, we've all seen, for example, old car headlights with water inside, and that means that they're usually past their life cycle, because under normal circumstances that headlight has been tested. Okay, a very common, especially in electronics, is solder fatigue. Okay, so the continuous heating and cooling of the sample may lead to solder fatigue, and this is a very common cause of failure of products every day. And then finally, plastic or display degradation. So we buy a product that comes out of the shelf looking and behaving in a certain way, and if we leave it frequently in the sun, the plastics will start to degrade, color will start to come off. Sometimes it doesn't. It was transparent, it becomes non-transparent with time, yellowish. So all of this may be anticipated and may be tested. And some of the tests that we conduct, or that our users conduct, better said, are listed below. Okay, so thermal cycling, of course, this is by far the most common one. So thermal cycling is exactly what it says on the tin, which is submitting a sample to cycles of high and low temperatures. Okay, it's very important that of course, in an environmental chamber, we control the air temperature, but it's very important to note that we may also add additional sensoring to control the temperature at the sample. Okay, so it's common, for example, when we are testing not for a component, but rather an assembly, that there's a measuring of temperature inside that assembly to see how well it's behaving versus outside conditions. So this is temperature only. We can take it to the next level and do climatic cycling, which is the same concept but with temperature and humidity. And so this will, for example, damp heat is a very, very common test. But also, drying the samples, going to lower temperatures. The automotive industry, for example, the standard is -40. In our aeronautical industry, we can take samples down to -75. So all of this helps us determine whether or not that equipment is sturdy enough. Also, a very common example that I think allows you to understand what climatic cycling is. Can you imagine the probes on the nose of an airplane that are, they're flying at -50 for 8 hours or 10 hours or 12 hours? And then if they have to do emergency landing in, I don't know, Saudi Arabia or a very, very hot climate, in a matter of minutes, they may have to go from -50 to +80. Okay, so this is very common, and this is one of the main uses of climatic chambers. And then we start going into more, let's say, demanding tests. One is vibration plus shocks plus climatics. So it's exactly what I've been presenting, but adding sine vibration, so a frequency that is defined by the users, or a set of frequencies, or a certain pattern of vibration, and sudden shocks. Okay, so I'm thinking some examples from the past that we have been dealing with include, for example, the antenna from cars or trucks. Okay, it's a very small component. Unless we are in the automotive industry, we hardly think about the the antenna, but it's actually a very delicate and complex component of the car or truck. Okay, so there's a very systematic set of tests that we have to conduct on that particular component. Of course, dew point condensation, I've already addressed this, and thermal shocks. So thermal shocks are a subset of climatic cycling, okay, or thermal cycling, better said. So climatic shock is a sudden variation of temperature, but much faster than what I was describing before with the airplane example. Okay, so we're going to see in a minute. In a thermal shock chamber, we provide cycles. You can do, 1,000, 10,000 cycles of hot, cold, where from one temperature to the other one, it doesn't take minutes, but it takes seconds. Okay, so it's a very harsh shock to the samples, and this is usually a survival test. So you put 100 samples in and you see how many survive, and that's what drives decisions afterwards. Okay, so this is an overview of the type of testing that we are mostly involved with. We've also been involved in the past with water ingress, for example, which is also critical. But water ingress is less connected to climatics, so I'm not going to focus as much on it. Same thing with, for example, salt spray. Okay. So going forward, how do we ensure that our users have capacity and the conditions for this performance? And I'm being mindful of time, so I'll keep going. But essentially thermal cycling. Okay, so thermal cycling, the reason why I'm putting here the volumes from 300 to 2000 liter volumes is because depending on the industry, of course, every industry has standards, and even within the industry, every manufacturer sometimes have their own standards. But usually the process is that you start with a component, then you test a subassembly or an assembly, and then you can test the whole set. Okay, so taking the case of a PC, for example, you would test the motherboard, and then you would test the whole PC. Why? Because the component individually has to be analyzed, but then when you assemble it in something else, there may be interactions between components that you were not previously aware. So a very common case is the GPS or the radios in our cars. They're individually tested, but when they are applied to the dashboard, they start to have interactions with other components, and there may be localized hotspots where temperature spikes, and so they have to be addressed. Okay. And by the way, we do this in a climatic chamber. And then in the end, for example, the whole dashboard may go to a vibration chamber where the whole thing is shaken, so that we make sure that, everyday life, uh, it's sturdy enough. So in thermal cycling, again, small to medium components. The temperatures I've already mentioned, we usually people start from -75 all the way up to 180 positives. Several speeds available. These are the standards, but upon request, of course, several different speeds may be available, and the volumes that I've addressed. So this was thermal cycling. What about thermal shock? So in thermal shock, again, same reasoning, several sizes available. And the thermal shock, the difference is, I don't know if you can see my mouse, but there's a basket inside of this chamber that goes up and down. So there's a hot chamber and a cold chamber. The hot chamber can go up to 200 degrees, and the cold chamber can go down to -70. And then this basket goes up and down the number of times that you want, and it promotes a shock. Okay, so it takes 5 to 10 seconds to go from one position to the other one, and it just goes like this many times, and to determine the survival rate. Small samples, usually low mass, so individual components, PCBs, very small assemblies, usually electronic components, rely heavily on this test. Now, sometimes we forget that in electronics, in the electronics world, the cabling also needs to be tested, right? So we tend to usually think, PC or cell phone, but the cabling also needs testing. And for example, I'm looking at my PC, the monitor goes up and down. The cabling that is in this hinge has to be tested. Okay, so we move to integrate not only the climatics, but also, especially for cold temperatures, also automated testing rigs. Okay, so in this case, there are standardized mandrels and weights, and it just coils and uncoils the cables a given number of times. Okay. Moving on, battery testing. Again, my PC has a battery. Okay, so all the batteries from your cell phone to even your clock, to the car that you drive or that you may drive, all of those have to be tested. And when you get to much bigger car battery sizes, powerful batteries, then they have to be carefully tested, because there are risks that are associated with this battery testing that have to be accounted for. Okay, so depending on the level of risk of the test that you're conducting, these chambers can also be fitted with safety equipment that matches the test that we're going to conduct. Okay, so usually EOCAR levels from 1 to 6 are available, and then usually also these chambers are integrated with battery cyclers that ensure the test from the battery supply point of view. Okay. Solar, UV, and radiation. So I was mentioning, what happens if you put your cell phone on the dashboard of your car and you go to the beach and you forget about it, and what happens when you come back. Okay, so that is also tested, usually in this type of chamber. It must be noted that the chamber still has the full operating capability, but usually when the light is exposed, that capability is decreased. So usually it's operated from -40 to plus 80 degrees Celsius. And then the light itself can be UV, visible, infrared, a combination of all these. They can be adjusted. Since we're focusing on electronics, up until now we've mentioned very small chambers, but all of this that I've been presenting is available in much larger chambers. Okay, so from small reaching units to big walk-in units, that is also doable. and you have some pictures here as well. So vibration and climatics testing. So again, we are joining climatics, temperature and humidity, cycles of temperature, humidity with vibration. And then vibration can be a simpler sine vibration, or it can also have shock vibration. Okay. So in this case, what we do is we work closely with our users, with the shaker suppliers as well, to determine how the chamber and the shaker interact. But this is very, very widely used, especially in companies that the cases we know the best are companies that are suppliers of the automotive industry. Okay, they're not the manufacturers directly, but they're usually electronics companies that supply automotive industry or components for other industries. And the final note is that the shaker can be vertical, horizontal, or multi-axial shaker. Then it depends on the specification of the users. And my last slide is driving chambers. So again, everything that I've been presenting, usually when we talk about electronics, we talk about very small. But as I mentioned, we've operated in the car industry, we operate in the aeronautical industry, even train industry, and those components tend to be much, much larger. So everything that we do in reach-in has to be also sometimes, remember I was mentioning before, component, assembly, sometimes final product. And I think the cars are a very good example of that, where maybe you do an electronic board, then you do the radio, then you do the dashboard, but finally you have to test the whole car. Otherwise, you never know. And usually these big walk-in chambers are also integrated with other components that we've just seen throughout the presentation. So we can do crash testing, radiation, shakers, of course, dynamometers, or battery testing. Okay. So I don't want to over explain at the moment. Thank you very much for your time. Just, final note is that the possibilities for environmental testing are limitless. The big part is defining exactly what users want, what they need, why this makes sense, and then I would say designing the chamber is usually the easiest part. So thank you very much, everyone, for your time, and I'll be fully available for your questions.
Great. Thanks, Jal. That was really interesting. I find environmental testing to be a really interesting subject. I'm just going to start by asking you, like, but in terms of consumer electronics, what kind of products are you typically testing?
Well, we've worked. I'm not going to mention brands, but we worked with the very well-known electrical car manufacturers. Okay, cell phone, even a Formula One company, which I think was interesting in their case, for example, they wanted to test powertrains and the integration of hybrid applications. So I would say, yeah, usually we do components. Sometimes we also do end products. So cell phones, PCs, electrical vehicles. That's more or less the range where we operate in.
Yeah, I was just going to ask you about that, actually, components versus end products. Is there a difference in terms of what's being tested when you're testing a component versus the final product?
There is because I would say the component. Well, obviously, 80% of the times the component is a lot smaller than the assembly, right? So when the size of the chamber, of course, is a variable, an important variable at that. And when we do the component, it's also tends to be a simpler test because you're looking at simpler failure modes. Okay. When you're doing an assembly or a product, you're looking at interactions between components. So the example I was giving throughout the presentation is when you put your radio in the center of the dashboard, and you put the whole set with a big screen and so on. When you're doing it alone, it's not interacting, for example, with the AC piping that's behind it, right? So let's say you're simulating a hot sun day for the radio, and you're simulating 60 degrees. Okay, but what if then somebody makes a mistake in the car or for some reason wants it and they put heat at the full power? Okay, so maybe instead of 60 degrees, we're now looking at, maybe 70 degrees. So all of that adds up. And I would also like, because I think this is important, which is how representative is testing versus real life. Okay, and we've seen, for example, I remember a few weeks ago on the news on the news an information that Airbus was having some issues with one sensor, and I believe it was, I'm talking from memory, but I believe it was a radiation sensor that was in some conditions wasn't measuring correctly, and they had to intervene in some airplanes. So it was big enough to make it to the news a few weeks ago. And my point is, there are chambers for radiation testing, as we've seen, right? But if the angle of the radiance or something in that test was done in a certain way that was not exactly representative of a situation that was happening in real life,
Mm-hmm.
the test that we actually conducted in the was not super representative. It
Mm-hmm.
doesn't mean that there was not enough care, or they skipped something that they should have done. It just means that testing sometimes also has blind spots that you only know afterwards.
Yeah, I understand. Yeah, and just to pick up on that, then, who who is sort of like taking the lead in directing that kind of understanding? Is it that is this something that it needs that is constantly being revised in the standards in terms of like understanding? Okay, this is actually how people use this product, so we need to test it in this way. Or is it the companies themselves, or is it the test services like you who
Yeah.
are recognizing this?
No, usually, I mean, that particular case, as is usual, for example, in car recalls or stuff like that, is it comes from somebody in the market after the product was in the market.
Yeah.
Somebody identified a weak point, and then it usually starts in the company itself, and then revising an international norm is actually something that is not easy to do, and it takes the agreement of many moving parts, let's say. So I would say definite from the cases we know, this is usually driven by our customer, which is usually the company that
Hmm.
want to manufacture a better product or correct something that they've seen that is not working well, or they want, even, for example, there's a technological breakthrough or a regulatory requirement. So let me give an example. If there are any people here today that operate in the refrigeration industry, they will know that there is a new F-gas legislation in the last year or so. Okay, that meant that all manufacturers of air conditioning units had, some of them had to change their refrigeration systems. So that this was environmental driven, let's say. It means that they have to change their technology, and suddenly they have to retest everything because the technology changed. They have to basically develop a new product.
Hmm.
So it may be driven by regulatory. It may be driven by market demand.
Yeah.
It may be driven by the need for correction of something that went wrong.
Yeah. Yeah. Is are this is a bit of a broader question, but in this age of more and more computational power inside of electronics, and therefore they're carrying more and more of these microchip systems within them. Are they more susceptible now to the environment, carrying all of this like sophisticated like um, soldering and rare metals within them?
Well, I don't. To be honest, I don't have data if they're more susceptible or not. What we see is that the systems are increasingly complex. So they're becoming more and more complex. Take your cell phone, for example. Your cell phone, you know, 30 years ago, your cell phone was, one color screen with a few keys and very simple operation. And today you have a laptop PC almost in your pocket, right?
Mhm.
So it's one of the most, let's say, frequent examples of higher complexity. But you can take it to cars, for example. Okay, an EV today, any EV today will charge over 100 kilowatt power at charging station, right? Some of them charge at a lot more power than this, which means that a single EV has a connection power to the charging point, which is bigger than many apartment blocks. Okay, so this is ever increasing complexity. Okay, and I would say on the positive side is that also regulatory and uh, company uh, acceptance of error has decreased, which means that things get tested a lot more than they used to be.
Yeah.
Okay, so there's this I would say mutually fed cycle, which is on the one hand you have more complex systems. Because they're more complex, they have to be tested more, which in turn leads to also more innovation breakthroughs, more complex, and so on. So
Yeah, yeah, I see. And but this factor of complexity means that there's more and more things working interoperably, and more things, so that
yes,
there's more factors that you have to take into account, which is what you were talking about with the car and the air conditioning unit behind it, and
correct.
yeah, um,
Ha- Paul, just a quick note. This is the reason why ultimately, despite our simulation software has never been more powerful than it is today, right? So every manufacturer has, they can assess structural integrity, they can make computer fluid dynamics, um, forecasts, and so on. But in the end, you always have to test the real product under real life conditions. So,
yeah.
for example, let's go back to the car example. You design everything, you can do all the calculations, and people do the calculations. They will test in the chamber, but after that you will see test vehicles in the roads being tested for 1 or 2 years, maybe for hundreds of thousands of kilometers, right? Because in the end they will have to go to real potholes and twists and bends and highways and so on.
Hmm. Yeah, and there's things you just can't predict.
Exactly.
Um, and then I wanted to just ask you about how the how customers respond to environmental testing. Do you find that there is growing recognition of its importance?
Well, I would say, well, starting by the end of your questions, definitely. So environmental simulation is growing more and more. It's one of those markets that you feel that this. How shall I put this? Everything's been discovered. You don't need to test anymore. At some point, everything will be tested. There's no point in testing it anymore. And yet, what we see in the real world conditions is exactly the opposite. Is you test more and more, you accept failure less and less, right? So that means that you have to increase the testing. Sorry, my dog's acting up. But you have to increase your testing conditions to decrease failure as well.
Yeah, yeah, I see. And so I'm just going to look at. I thought that would be a nice moment to look at one of these polls, because we have the results of the 4 polls that we put out. One of the so the first two, well, the last 2 polls actually were. The question was, instead of buying a chamber, I prefer to either get a service from a specialized lab or rent the chamber only for the duration of the test. Now, 100% of the responses were A, get the service from a specialized lab. What do you think about that in terms of how customers then understand
I
environmental?
think it makes total sense.
Yeah.
The poll question isn't innocent because a lot of our main users are actually not the end brand. It's actually the testing platform that supplies to a number of brands.
Mm-hmm.
This makes total sense. Why? Because let's say you're a brand that has developed a new model of anything. That means if you have 100% of that testing capability in-house, you have to dimension the testing capability to 100% of the lot size that you're going to test.
Mm-hmm.
Which means that after that peak of new product design, you're going to have your chambers probably sitting under 100% usage rate. So they're sitting idle some of the time. So what we see most often is manufacturers will have a set of chambers for their day-to-day operations, for their, let's say, short-term testing. But then when they're designing a new product or R&D applications, they will more frequently go to testing platforms because they can, have a wide range of testing rather than having to buy all that capex and hold it in-house.
Yeah, yeah. Are there certain very big multinational corporations that would prefer to do most of it in house? Maybe because of also like privacy and IP concerns, that kind of stuff.
Well, I'm sure there are, especially in the defense sector. Secrecy is the name of the game, right? So I'm sure there are cases like this. I would also add that these in the international testing platforms, if they, I mean, I don't belong to any of them, so I feel a bit free to say this because if there ever was a leak of information to a competitor, they would be out of business, I suppose, right?
Yeah.
Nobody would buy their services anymore.
Mm-hmm.
So I suppose from their end, they take great care. Uh, well, let me give you an example. I will give you a real world example. We worked with a testing bed a couple of years ago, and they were testing an airplane component. Okay, and they were doing it for an international customer, and their testing bed was completely independent from the rest of the building. None of the PCs that were testing that specific component were connected to the rest of the network of the building or internet. And the data that was generated by that test was sent to the customer by two people in different days, and none of them had access to 100% of the data.
Mm.
So this is the most extreme case I know.
Yeah.
I'm sure this exists a lot because you can imagine imagine a Formula One company and they have access to, I don't know, wing design or something ahead of time, which is a huge advantage. So I know that secrecy in a lot of industries is the name of the game, both for the customers but also for the testing platforms that are conducting these services.
Mm-hmm. Okay. I'm going to have a look at another one of these polls, Zhao. Just before I do, though, I just wanted to say if anyone wanted to put any questions into the Q&A, please do that. I'm also going to move my computer because I noticed there's a light shining on my face. Try and get that away. Yeah. So another one of the polls was the most important factor when deciding to purchase a climatic chamber, and 60% said price, and then 20% said specification, and 20% said close technical support. So do you want to just comment on that, Jan?
Yes. Well, of course, we are suspicious because we are manufacturers of climatic chambers, but I would say, well, that pretty much aligns with what we see on a day-to-day. Our opinion is that poll should be the other way around. So actually, very close technical support is extremely important, and specification the same thing. Even more than price. And let me give you an example. Let's say you have an automotive or a product line, and you're removing samples out of that product line and testing them to see if that product has the quality assurance that it should. If the chambers fail, the testing chambers for the quality applications fail, that means that whole lot has to at least wait until uh, the error or the problem is solved. And so it may produce really big logistical challenges. Okay. So actually, I would say our policy is usually to have a great price after ensuring performance and that you have all the service nearby that you need.
Mm-hmm. Yeah. Okay, that's interesting. Yeah. And we have two more polls, but I think we'll just go to those a little bit later.
Mm-hmm.
I wanted to also ask you about the question of the limits, because I noticed when you were going through, you were talking about this cycling, thermal cycling and thermal shock, that they had different temperature limits, and I
Mhm.
wondered like how those are defined, who defines them, and why those particular limits.
Well, usually it's driven by either a norm that they have to follow or the intended use of the product.
Mm-hmm.
Okay, so with of course a given margin for safety, but that's usually the where the operating limits come from. The chamber can perform from, I don't know, -75 to +180, but let's say that you're selling. So let me give you a real world example. We have testing chambers like this simulating medicines when they are shipped via airplane. So let's say you have a shipment of, I don't know, antibiotics. They have to be shipped via airplane to the other side of the world. As a laboratory, you have to test them to make sure that they survive, the conditions of the airplane. Okay. So of course you're not going to test to plus 80 degrees. Okay. What you're going to do is to test for negatives, and maybe 20, 30, 40 degrees, which is when the airplane is on the runway. Uh, so that's a real world example of, the chamber can be much more powerful, but ultimately the temperature range is driven by the application.
Mm-hmm. I see. I see. And what about you talked about the scale of the chambers being different depending on the size of products that you're testing, but you gave some very the very big examples of like the huge chambers that you have to test cards versus
Hmm.
like
Hmm.
smaller chambers. But I'm just wondering, like in terms of a lot of electronics, certainly a lot of the electronics that we cover in the magazine are going to be smaller in scale,
Hmm.
but
Hmm.
there's still going to be variances. There's a big difference between the size of a smartphone and a lawnmower or something like
Hmm.
that. So do you? What are the different dimensions of the chambers at the sort of smaller scale?
Yeah, well, I mean, now this varies from manufacturer to manufacturer. In our case, for example, our smallest unit is 30 liters, so it's the size of a very small backpack. And usually it's, PCBs. We know that cell phones have been tested in those applications as well. So very small components. They're, very small in size. That chamber can go down to -60, for example. So the chamber is small, but it's still very powerful. And then, for example, we can move to the other side. I mean, I don't know if we could consider a private jet the consumer electronics, but you know we can have chambers where we put the whole private jet minus the wings inside, because then we have to test um, for a lot of conditions. So uh, anything in between, it's doable.
Hmm. And are you testing also? I remember once writing a feature about outdoor electronics versus indoor electronics, or electronics that might be used in more kind of rugged environments. So if you have sort of those ruggedized watches that people take on these endurance runs and that kind of thing. Do you do a lot of testing with outdoor electronics, and are you thinking about you're obviously thinking about how the electronics is going to be used in terms of what the testing will be?
Yes, well, I wouldn't say we do a lot, but we do something. So
Yeah.
usually, what outdoor we've done chambers where we have rain simulation, for example, freeze and thaw applications, um, infrared, UV, visible light degradation. We've had chambers where we simulate snow and ice, for example. So I would say, depending on the demand, it really, from the technical point of view, I would say a lot of it is doable. I wouldn't say anything is doable, but a lot of it is doable. We just have to get the specification right and have a clear view on what the intended outcome of the research is.
How do you simulate snow?
Very interesting. Well, actually, snow is a mix between air and water. Otherwise, if you just blow water to the sample, what you're going to get is ice, right?
Mhm.
So what actually you have to do is a mix between air and water at a certain temperature with a certain airflow, very low temperature airflow coming in, so that you have those flakes falling evenly on the samples.
Mhm.
Okay. We've had, for example, we had some users requesting 30 centimeters of snow on their samples because that's their real life scenario. Okay.
Mhm.
And it's interesting because they started years before, testing small scale and simpler in temperature. And then gradually they moved on because their product line was increasing. So they moved on to more powerful, bigger equipment with more demanding applications as well. Okay,
Mhm.
so it's important.
And are you typically testing to failure?
Well, that I don't know. Why? Because we don't. Our, let's say, our base of knowledge ends at the user's door. What
Mm.
they do inside the chambers is often confidential, and we don't have access. Nor do we have to have access to
Yeah,
that data.
I
What
see.
I can tell you is there is one product application where we have to know whether or not it's a destructive test. That's usually battery testing. So in that case, I would say not the majority, but a lot of the chambers that we manufacture, they don't go to explosion stage, but they go to very destructive stages. So up to ILCAR 6.
Yeah,
There is a seventh level of ILCAR, which is explosion. So you really want to make an explosion. That we don't do. We do up to level 6 uh, by choice.
yeah, and you need to know that level. You need to know the level of destructiveness for what reason?
Yes, because the level at which you want to take your sample and the components on that sample will determine, for example, the protections that you have for people working with those samples.
I see.
Even the hinges on the door have to be different. There has to be an So let's say that you're planning to go up to level 6, but in reality there was an explosion. Okay, for some reason it went wrong. There
Mm.
has to be a way of that explosion gas to escape, usually upwards rather than forward where a user might be sitting or facing the chamber, right?
Mhm.
So we have to account for safety above all, and it really helps us if we know in advance for example, what the component composition of the batteries is, because then you're looking at specific gases. A battery before combustion, a battery will start releasing gases, right? So
Mhm.
that's the moment you want to analyze, and if that's not your goal, stop everything.
Mhm.
Okay. But then there's emergency venting, uh, fire extinguisher, a whole set of equipment that we can bring in to make sure it's safe.
Mhm. Yeah. Okay. We've got two more polls that I wanted to look at before the end. There was a question: was which of the attendees know of Aralab? And 14% did.
Mhm.
86% didn't. What do you got to say about that, Zhao?
Well, that's what we're here for, right, Paul?
Yeah, absolutely. Yeah.
Let's change that. I mean, it doesn't surprise me a lot because even though we're doing this for many years, we have I would say, a very stable reference and customer list. So we're happy about that. But we want to grow, and that's what we're here for. So I think it's time well spent because now 88% of people already know what allow, and
Yeah.
if they ever need something in the future, please let
Yeah.
us know.
Yeah. And then we also asked whether or not those watching have used climatic testing, perform it, sorry, in their day-to-day role. And 50% did and 50% didn't. So about half of these people are doing environmental testing.
Well, my comment is that maybe half of the people watching us right now, maybe that their function description doesn't include testing. Okay, so or the industry that they're working on or the projects that they typically work on don't need testing, at least until now. What I would say, food for thought. keep this in mind if there's ever a requirement. Um, look into the processes that you're involved with, see where climatic testing might help. We always say that, climatic testing isn't a silver bullet. It's not going to solve all your problems, okay? We always ask, where's the bottleneck on your process, and why do you think, climatics can solve it? What is the issue that you're looking for, so that climatic can be added value? And then it's an engaging conversation with the users, and sometimes it's not applicable because what they really need is something else. Sometimes it's applicable, and if we're lucky, we're the ones they choose. Otherwise we'll meet same day in the future.
Yeah. And in terms of talking about the future, how do you see climatic testing developing in the next 10 years?
That is a very good question, Paul. And I wish I knew the answer, because I would be, a richer man if I did. I would say two things. One is I see it growing steadily as is, meaning, as I was saying, you get more and more products being tested more and more thoroughly, and then new products coming in every day which need additional testing. So I would say the baseline of the industry should keep growing in years to come. Okay. And I also want to uh, bring something that people usually don't think of, but we think about this at our lab frequently, which is sometimes our competition is not only other brands of climatic chambers. We have good competition, by the way, which we're fortunate that competitions also, helps us improve. But I think all of us as a group of manufacturers of climatic chambers, we will see in the years to come competition from what we call in silico uh, testing, which is simulation in the PC. So not
Mhm.
simulation in the real world, but
Yeah.
simulations being run based on historical data, and at least allowing you to for a broad range, for a set of parameters, really good predictions may come out of it. So I would say, the industry as it is will grow, but it's likely that we're going to see some more newcomers coming in that we don't know about yet, and they will be able to bring AI and big data and so on into our industry as well.
Yeah. 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 I mean, that does seem to be a pattern across industries, that there is a move to more and more simulation.
Yeah,
But like you say, it seems like there will always need to be a role for physical testing.
it is. It is, but let me give you an example also that we're involved with. But this is plant research. So there's a subset of plant research that is, it's called phenotyping. It's basically digital imaging of plants and trying to
Mhm.
determine specific traits on those plants before they're visible to the human eye, or that they make correlations between sample sizes and so on. And what happens is that you grow a lot of plants under controlled conditions where you change slightly one condition, and then you have a lots of data, you generate lots of data, and at some point, hopefully, hopefully you start to make predictions. What if I grew a plant in this way? Likely, like 90% confidence interval, the result would be this. And this, I think, is bringing this to consumer electronics. We already have really good CFD, so computer fluid dynamics software. We already have really good material structural engineering software, okay, to calculate stress and so on. So I think the logical next step is that we start doing predictions based on in silico rather than real life, and then maybe for special projects or final validation we will still do end of life, but more to calibrate the previous model than to develop, uh, let's say, product validation in itself. So
Yeah.
I would say this would be a whole different conversation,
That's
but
yeah.
for us it's really exciting.
Yeah. Yeah. Okay, Zhao. Well, I really appreciated your
Anytime.
being here. Yeah, thank you so much for talking to us, and thank you everyone who stayed to listen to the discussion. And thank you for your insights and responses in the polls and questions. Yes, and the presentation will be available also afterwards. It's being recorded, so you can follow it afterwards if you need to. So yeah, thanks so much, Zhao, and I hope you have a wonderful rest of your day.
You
Thanks for
too.
taking.
Thank you very much for having me, Paul. See you soon.
Okay, bye now.